When we have a sketch or a diagram of a galvanic or a voltaic cell, it's important that we know the main features and that we could give at least a rough rudimentary sketch of what this would look like. So in this example, we have the net ionic equation for this redox reaction between zinc and copper. And so what we want to be able to do, we can see itemized in the bulleted list here, is to label the different electrodes, identify which metal is serving as which electrode, the ions present in solution, what the reactions are, rather the half reactions for each compartment of the voltaic cell, show which way the electrons are flowing, which way the ions are going. And so what you see at the bottom is kind of a template drawing. It doesn't necessarily have to be quite as sophisticated. It's kind of a rudimentary drawing in the first place, but like your beakers don't have to look actually like beakers. You can do pretty much everything with rectangles, but you should have some semblance of two separate beakers or containers. These would be your half cells. In each of those, you'd have a rectangle representing the metal electrode. Those should be connected externally with a line, which would represent your wire. In the middle here is typically where we would indicate the voltage or the like a voltmeter. And then the other important thing is that connecting the two half cells, you have what we would refer to as a salt bridge. And that is what's going to facilitate the flow of charge and charge remaining equal as the voltaic cell is running. Without that, you will not get any voltage whatsoever. So whether you have a nice template like this or you do a quick sketch on your own, you have those main parts, the electrodes, the voltmeter and the wire on the outside, the salt bridge, and your two half cells. We're ready to go. So when it comes to labeling the anode versus the cathode, it's really up to you which one you call the anode, which one you call the cathode. It really does not matter. Conventionally, though, the anode typically is going to be on the left and the cathode on the right for a very good reason, which we'll see in just a moment. So I'm going to call the left one the anode, the right one the cathode, and that's the first one done. Okay. So then the next thing is to identify the metal that each electrode is made of. Well, remember, an ox and a red cat. Anode is where oxidation takes place. Reduction takes place at the cathode. So for my anode, I'm going to look at my equation, and I see that zinc is going from a charge of 0 to +2. Right? Copper is going from +2 to its elemental form, so going to 0. So oxidation is a loss of electrons, which means the charge is becoming more positive. Zinc is going from 0 to +2, so zinc is what's being oxidized, and therefore zinc is serving as my anode. That means that copper, right, going from +2 to 0 is being reduced, and what's being reduced is showing up at the cathode. So that part is done. Okay, the appropriate ions present in each solution. Well, in each half cell, you have the metal, okay, and then you have the ion form of that metal. So in the anode compartment, the left-hand beaker here, we would have zinc ions floating around in solution. And in the cathode compartment, we would have copper ions floating around in solution. All right, the half reactions for what's occurring. Beneath that, you would have zinc solid going to zinc ion in solution, producing 2 electrons, so that's your oxidation. And then in the cathode compartment, you have the copper ion gaining 2 electrons and coming out as solid copper. So there's our 2 half reactions. The electron flow is always from the anode to the cathode, fat cat. Okay, so you would just simply write E- for electrons and draw directional arrows showing them passing through the wire in that fashion. And then the last thing to do would be to show the direction of ion migration via the salt bridge. And so you don't necessarily need to have it as complex as what I see here. Notice I don't even have formulas per se, but I do indicate that the particles have a particular charge, either minus or positive. And so the thing to remember with ion migration is that anions are going to flow into the anode compartment, and cations are going to flow into the cation, or cations are going to flow into the cathode compartment. Now those voltaic or galvanic cell diagrams are nice, but they take a little bit of time to write. And so there is another way that we can represent a galvanic cell in a much more condensed, streamlined format, one that we can actually just type in and not have to worry a whole lot about special features or diagrams and things like that. And that's known as line notation. And so line notation is going to take on this basic form. You see some vertical lines in there. You see some notations where we have some things that are solid, things that are aqueous in solution. And remember how I said in the voltaic cell diagram, typically we put the anode on the left. Well, the reason that we do that and put the cathode on the right is because in line notation, the anode is on the left-hand side and the cathode is on the right-hand side. So if you kind of stay consistent, it makes it easy to go in between the different formats. All right, so what do those lines represent? Well, the single lines represent the barrier or the interface between two different phases of matter. So for instance, the first solid here would be the anode metal, the electrode, okay, and then the barrier, the interface between that solid metal and the ions that are in aqueous solution. Same thing over here on the cathode side. You have the ions in solution that are gaining the electrons and therefore turning into the solid form. They are plating out. The double line represents that salt bridge, or sometimes it's referred to as a porous disk. But basically that is what is allowing the passage of ions from one compartment to the other, which is maintaining that charge balance. Now, in some cases, what you have being oxidized or reduced may not plate out as a solid. You may have reduction of an ion from one oxidation state to a lower oxidation state, like iron 3 to iron 2. And so when that happens, the setup is the same. Okay, you still have solid, single line, the aqueous species. But then here on the cathode side, we can see that we are reducing iron 3 to iron 2. Well, both of them are in solution. So they're both going to be to the left-hand side of that single line in that cathode compartment. But they still need a surface, an inert surface for them, for that electron exchange to be able to occur on. And so that is frequently we use platinum for that. And so that's why you see PT in the solid state in the line notation here.